Good day and welcome back. This is the second installment or part 2 of our discussion on the limit of a function. So in our previous video we introduced kind of more of this intuitive definition of what this statement or mathematical symbols mean. We say the limit as x approaches a of f of x equals L if when x is close to a, the function output is close to L. And in this video, what I'd like to do is give a more formal or precise definition, point out some of the subtleties involved, investigate it graphically, and then apply it to an example. So the more formal definition is we say the limit as x approaches a of f of x equals L, if we can make the values of f of x arbitrarily close to L, so once again that's just close to L, by taking x sufficiently close to a. And that first part of the statement, is almost what we were saying before. For x close to a, f of x is close to L. The really important part I want us to focus in on is the end of this. So the on either side, but not equal to a. So when we say not equal to a, the important observation that we want to make is it does not matter what happens at a. That is to say, anything can happen at a. The function might not even be defined there, or the function output could be something totally different from the limiting value. So not only does it not matter, f doesn't even need to be defined at a. So let me go ahead and sketch out a few graphs that illustrate the important concepts that we've mentioned. So I want to draw several examples, illustrating when the limit is L, but seeing kind of different behaviors with the function value at L, to really emphasize that it does not matter what happens at a, it just matters what the function is doing close to a. And that's a really, really important part, so I'm going to emphasize it again. It does not matter what happens at a, it only matters what happens for inputs close to a. So the first example I'm going to draw is just something like this, and we'll let L be that limiting value. So in all three of these graphs, they're going to illustrate the limit being L. For an input close to a, if you trace up, you can see that the outputs are close to L. So in this case, if you wanted to draw that in for something close to a, we can very clearly see the output is close to L. And in this first picture, note that the function output is also equal to L. But that certainly doesn't need to happen. I'm going to draw the function a bit differently now. So I'm going to put an open circle at a, and then way up at 100, I'm going to put a closed circle. So once again, the limit as x approaches a of this function f of x is equal to L. And we can see this intuitively by just noting if you substitute in an input close to a, the function output is going to be close to L. But in this case, the function value at a is 100. So it's not equal to L. So it really doesn't matter what happens at that value a. It's just what happens close to a. And similarly, if we wanted to take this even a step further, we could even make f of a undefined. So in all three of these examples, the function in blue is the function f of x, and in each case, the limit as x approaches a is L. The function value could be equal to L at a, it could be defined and be a number other than L, or it could even be undefined. So it really does not matter what happens at A, only what happens for inputs close to A. So let's go ahead and investigate an example that will lead us very nicely into our next property and be the starting point for part 3 of this topic. So consider the function f of x, which is piecewise defined. So it's going to be the function x when our inputs are less than or equal to 1, and the function 2 when x is greater than 1. And maybe the best thing to do to get started before even finishing the question is to sketch a picture. So we will, somewhat frequently as we talk about limits and our upcoming topics, we will use piecewise defined functions. So what this is simply telling us is if we are looking to the left of or at 1, we want to sketch the function y equals x. And if we are looking for inputs closer to 1, or excuse me, above 1, we want to sketch the curve, or in this case the line, y equals 2. So when we are at 1 or to the left of 1, we have the line y equals x. From 1 onward, so I'm going to put an open circle up here at 1, we can only have one output associated with each input. We have the horizontal line y equals 2. And now that we have a graph of the function drawn, I want to go back to the question that we were asking. What is the limit as x approaches 1 of the function f of x? And I want you to maybe pause the video. This is something I'll ask you to do frequently. Pause the video, give yourself 30 seconds, a minute, see if you can come up with an answer. So just a simple yes or no, but then a small amount of reasoning to go with it as well. Okay, so I'm assuming you've paused your video and you've thought about this. If you didn't, now really pause the video and think about it for a few minutes. Now, when we ask the question, what is the limit as x approaches 1 of f of x, this limiting value needs to be a single numeric value. And the key there is it has to be a single number. You can't have two different numbers playing the role of the limit. It's a unique value. And the observation that you hopefully made is that this function behaves very differently to the left of 1 as it does compared to the right of 1. So let's see if we can put a few details into this. So for x close to 1 on the left, and it does matter whether we're to the right or the left of 1. So when we're close to 1, but specifically on the left, f of x, the function output, is close to 1. So if we have an input close to 1 on the left, the function output is going to be close to 1. And what this is getting at is the idea of a one-sided limit. So the limit as x approaches 1 from the left of f of x equals 1. And note, we've superscripted this with a minus sign because when we think minus, we're really thinking negative or to the left. So the limit as x approaches 1 from the left of f of x is 1. Now note, we can make a similar observation from the right. So we could say for x close to 1, on the right-hand side now, f of x is, I want to say close to 2, but it's actually even equal to 2. You can make a stronger statement. It's close to 2. So if you look a little bit to the right of 1, that function output is going to be close to 2 because it is precisely at 2. And in terms of symbols or notation, we would say the limit as x approaches 1 from the right of f of x is equal to 2. So in this case, we cannot make the values of f of x close to a single value of L. So for x close to 1, with no restriction on the sides, we cannot make f of x close to a single value. And note, 1 is not equal to 2. So this would be an example where we say the limit as x approaches 1 of the function does not exist. And the reason that it does not exist is because the limit from the left does not equal to the limit from the right. And I'm going to finish by just writing down a property that we will start off with in our next video. And the property is as follows. That the limit as x approaches a of f of x equals L is a true statement if and only if, so equivalent to, the limit from the left being L and the limit from the right being L. And what this does for us is it gives us a very convincing reason, like we've used above, as to when the limit does not exist. So this is really useful for showing that the limit does not exist. So the observation to make, and we'll make this again on a future video, is if the limit as x approaches a from the left of a function is not equal to the limit as x approaches a from the right, so the function is behaving differently to either side of a, then the limit as x approaches a of the function does not exist. That is, if the one-sided limits from the left and the right do not agree, the limit does not exist. And I'd like to finish this video by just noting that in a class like Calculus 1, and certainly beyond it as well, it's very important to justify and explain your work. So if we were asked what is the limit as x approaches 1 of this function, we would somehow want to indicate what the limit is from the left, what the limit is from the right, and use that to conclude that the limit itself does not exist. So a majority of this work, and you could lose some of the writing, is 100% necessary. But that's something we will continue to focus on in upcoming videos and examples. So for now, stay tuned and take care.